You tap an icon on your phone, and a messaging app opens immediately. It feels like a single, seamless physical action. But look at this image of exposed microprocessors. Beneath the smooth glass, your device is a rigid collection of silicon pathways and gold pins. It doesn't understand human gestures like swipes or taps. It only processes raw electrical currents, pulsing billions of times per second. If your web browser or messaging app were allowed to send electrical signals directly into that silicon, the results would be catastrophic. Applications are greedy by nature. Without supervision, a web browser would pull all available power, overwrite the memory space your music player is using, and crash the entire device. To prevent the hardware from tearing itself apart, every computer relies on a strictly enforced software middleman, the operating system. The operating system sits directly between you and the physical machine. It translates your human intent into an electrical reality the processor can execute safely. This diagram shows the architectural stack of a modern computer. We start at the top layer, which is the only part of the machine you actually see. This top layer is called the shell. The shell is the visual user interface, the desktop, the folders, the windows, and the menus. It surrounds the core software, providing a safe, graphical way for you to interact with the device. Sitting just below that shell are your applications. By design, these programs are entirely powerless. A word processor cannot spin up a hard drive to save a document, and a video game cannot push pixels to a monitor on its own. Still looking at the stack, notice what happens when an application needs to perform a physical action. It submits a polite request called a system call. This is a highly secure protocol where the application asks the operating system for permission to access hardware. Your apps are trapped in a sandbox. They can calculate data internally, but they rely entirely on the operating system to act as a secure proxy to execute any physical changes to the machine. This diagram maps exactly how that secure boundary works. The dotted line in the middle separates the application space above from the absolute core of the operating system below, known as the kernel. It operates in a highly privileged state, completely hidden from the user. When an application makes a system call, it triggers what you see here as a trap to kernel. The kernel intercepts the request, evaluates whether the application has the right security permissions, and checks if the physical resources are actually available. If the request is approved, the kernel steps in. It directly commands the hardware to perform the physical action, like reading a file from the disk, and then passes that data back up across the boundary to the waiting application. This strict physical separation between user space and kernel space is an intentional defense mechanism. If a piece of malicious software tries to delete a critical system file, it has to ask the kernel to do it. The kernel checks the permissions, recognizes the threat, and denies the system call. The kernel functions as an absolute dictator. By ruthlessly monopolizing direct hardware access, it ensures the computer remains stable, regardless of how many applications run. Processing a single system call is simple enough, but at any given second, dozens of background services, web tabs, and communication apps are screaming for the kernel's attention simultaneously. To handle this chaos, the operating system performs process management. It takes the CPU, the central processing unit, which acts as the main brain of the computer, and slices its attention into increments of milliseconds. It switches the CPU between tasks so quickly that multiple applications appear to be running perfectly simultaneously. At the exact same time, it performs memory management. The operating system carves up the RAM, the fast, short-term memory where active data is temporarily stored, and walls off specific blocks for each active process. This ensures your web browser's data never accidentally bleeds into your video editor's workspace. Finally, it has to manage all the physical hardware attached to the machine. The operating system uses specialized pieces of software called device drivers. These act like localized translators, taking standard instructions from the kernel and converting them into the exact bespoke language required by a specific printer, keyboard, or hard drive. Every millisecond is scheduled, every byte of memory is partitioned, and every hardware request is vetted. Without this relentless, microscopic bureaucracy in real time, the sheer weight of competing processes would instantly freeze the machine. This diagram pulls the whole journey together. Raw electrical current in the hardware is tamed by the kernel, formatted into a system call, delivered to the application, and finally displayed in the shell for you to see. This vertical trip from silicon up to the glass screen happens flawlessly. thousands of times every single second your device is powered on. Look at this image of the iPhone, iPad, and Mac. While they represent completely different physical form factors and screen sizes, they all rely on this exact same architectural stack underneath. The hardware changes, but the core strategy of separating the user from the silicon remains identical. The OS doesn't write your emails, edit your photos, or beat your high scores. But by rigidly managing resources and enforcing security, it creates the stable environment required for those applications to function at all. The physical processors and glass screens are impressive pieces of engineering, but the true marvel of modern computing is the invisible software bureaucracy that brings that dead sand to life.